In this video, we are going to talk about the first derivative and graphs of functions, and I've just introduced some new notation here. So the first derivative and the derivative are the same thing. We're going to talk about the second derivative in the next class. So when I say first derivative in this video, we're really just talking about the derivative. Okay, so we know the following. On the interval AB, if f prime of x, the derivative of a function, is greater than 0, then f of x is increasing. And if it's less than 0, then it's decreasing. Okay, so let's do a couple of examples. Let's find the intervals in which this function is increasing or decreasing. Okay, so if we simply start here and we go f of x, so f prime of x, the derivative is 8 minus 2x. All right, and we want to know when this function, the derivative, is positive or negative. Well, the easiest way to do that is to say, when can it switch from positive to negative? Well, that's when it's 0, because this is a continuous function. 8 minus 2x could also be when this derivative is not defined, but right now it's defined everywhere, so that's fine. So we get 2x equals 8, x equals 4, and then I tend to draw a number line. Put in 4. If I put in a very, very large positive number, then 8 minus 2x is negative, so the first derivative is negative. We'll put a little f prime of x here. And if we put in a very, very large negative number, this is positive. So our function is increasing. Negative infinity to 4 is increasing. And 4 to infinity, it's decreasing. Okay, so that was relatively straightforward. Let's look at another function. F of x equals x squared minus 6x plus 10. We do the same thing. We take the derivative, f prime of x equals 2x minus 6. We say to ourselves, when can this function, the derivative, change signs? Either when it's 0 or it's not defined. It's defined everywhere, so we'll figure out when it's equal to 0. So 0 equals 2x minus 6. So 2x equals 6. X equals 3. And then I use my number line. F prime of x. 3 is when it can change. If I put in a really big positive number, 2x minus 6 is positive. So it's positive when it's greater than 3. And 2x minus 6 is negative when it's less than 3. So we've got 3 comma infinity. The function is increasing. And negative infinity comma 3, it's decreasing. So this leads to the observation that the interesting points for this derivative, is when it's equal to 0. So we define a critical number as an x value, an x, where either the derivative is 0 or the derivative does not exist. So that's called a critical number. And again, from what we've just seen, a critical number is a place where the derivative can go from positive to negative or negative to positive, which means a critical number is a place where the function can change from increasing to decreasing or decreasing to increasing. It doesn't have to change from increasing to decreasing or decreasing to increasing, but it's a place where it can change. So that's what a critical number is. So let's find the critical numbers. So if f of x equals 1 plus x cubed, then we take the derivative. F prime of x is 3x squared, which means our critical numbers are where this derivative is 0 or undefined. 0 equals 3x squared, x equals 0. So the critical number is when x equals 0. Okay, f of x equals 1 minus x to the power 1/3. Then the derivative of this is 1/3, 1 minus x to the negative 2/3. Now, we set it to 0, 1/3, 1 minus x to the negative 2/3. And we observe, right, this is, if I rewrite this, this is 1 over 3 times 1 minus x to the 2/3, right? That can never be 0, so there are no solutions like that, but it's not defined when x equals 1. So there's a critical number at x equals 1. Okay, so there's our function. Okay. The value f of c is called a local maximum if there exists an interval ab containing c such that f of x is less than or equal to f of c for all x in ab. Okay, so what does that mean? It means we have a function. I draw my graph, and I have c, right? And here's a, here's b. Then f of c is the highest point. We call it a local minimum if there exists an interval ab containing c such that f of x is bigger than or equal to f of c for all x in the interval. So again, we'll draw this function. We've got our c, we've got our a, and our b, and it's going to look something like this, right? F of x is bigger than f of c for all x in ab. So those are called local maximums and local minimums, meaning you've got a maximum which is locally true. It doesn't mean the function doesn't go like this and become higher, and it doesn't mean in this case the local minimum that the function doesn't turn again and become lower. It means just in the region close to c, it is either a minimum or a maximum. Okay, these are called local extrema. Okay, local extrema and critical numbers. If f of c is a local extrema of the function f, then c must be a critical number of f. Okay, so that's our relationship between local extrema and critical numbers. So that gives us the first derivative test. If the derivative exists on both sides of a critical number c, then if f prime of x is bigger than or equal to 0 for x just left to c, and less than or equal to 0 for x just to the right of c, then f of c is a local maximum. If f prime of x is less than or equal to 0 for x just to the left of c, and f prime of x is bigger than or equal to 0 for x just to the right of c, then f of c is a local minimum. Now, it's easier to think of this if we draw some pictures. So let's have this as c. Let's draw a local minimum, right? So there's our local minimum. Now, if we look just to the left, we see the function is decreasing. If the function's decreasing, then its slope is negative, which means that f prime of x is less than or equal to 0. Just to the right of this local minimum, we can see the function's increasing. If the function's increasing, then f prime of x is bigger than or equal to 0. So function's decreasing and the function's increasing. So to the left it's decreasing, to the right it's increasing. We have a local minimum. Let's draw our local maximum. Okay, here's our f of c. Local maximum, we can see just to the left, the function's increasing. F prime of x is bigger than or equal to 0. Just to the right, the function must be decreasing. F prime of x is less than or equal to 0. Now, in the pictures I've drawn, f prime of c exists, and it must be equal to 0. Right? You can see the slope is 0. The slope here is 0. Okay, we can also look at a couple of other things. If the derivative exists on both sides of a critical number c, then if f prime of x is bigger than or equal to 0, just to the left, and f prime of x is bigger than or equal to 0 just to the right of c, then it's not a local extrema. Equally, if f prime of x is less than or equal to 0 just to the left, and f prime of x is less than or equal to 0 just to the right, then f of c is not a local extrema either. So let's draw these. Right? If we think about this, this means the function is increasing. Right? The function is increasing, not the derivative, but the function is increasing and increasing again. So if we look at that one, I'll draw a picture. the function is increasing and then increasing again. So here is C. Equally, we can have the same thing where the function is decreasing and decreasing again, right? So it's decreasing to the left and decreasing to the right. This C is not a local extrema because it's decreasing and then decreasing again. It's increasing and then increasing again. It's not a local extrema. So let's do a couple problems. We have f of x equals x cubed minus 6x squared plus 9x plus 1. Locate local extrema. What do? We find the critical numbers first. So if we want to find the critical numbers, we take the derivative. F prime of x equals 3x squared minus 12x plus 9. Set the derivatives to 0. 0 equals 3x squared minus 12x plus 9. We're going to divide by 3, so 0 equals x squared minus 4x, I can't divide, 6x squared minus 4x plus 3, which is equal to x minus 3 times x minus 1. This one I can just see, otherwise use the quadratic formula. So they're critical numbers x equals 3, x equals 1. So let's just draw our number line for the derivative. 1 and 3. All right, let's put in a really big negative number. If we put a really big negative number into the first derivative, we're going to have a positive number. Put a really big positive number into the first derivative, we're going to have a positive number. Choose a number between 1 and 3. How about 2? 3 times 4 is 12, minus 24 plus 9, that's negative. Okay, so what does this mean? We've drawn a number line for our first derivative. We know the first derivative is 0 at 1 and 3. We know the function is increasing below 1. We know the function is decreasing from 1 to 3, and we know the function is increasing from 3 on up. What does that mean? Well, we can just see here, right? If it's increasing and then decreasing, then we've got a local max at 1. Decreasing then increasing, that's a local min at 3. So we found our local extrema. The local extrema, of course, is f of 1 or f of 3. I'm not going to bother plugging those in and calculating those. Okay, here's another function. F of x equals x cubed minus 9x squared plus 24x plus 10. Take the derivative. Find the critical numbers. F prime of x equals 3x squared minus 18x plus 24. Set it to 0 to find the critical numbers. 3x squared minus 18x plus 24. Divide both sides by 3. X squared minus 6x plus 8. Let's look for 2 seconds. I think I can see that. So that's going to be x minus 4 times x minus 2. So we have critical numbers at x equals 4 and x equals 2. Draw our number line for the derivative. The two critical numbers where it can change signs are 2 and 4. Plug in a large negative number. The x squared term dominates. It's increasing. Plug in it's positive, sorry. Plug in a very large positive number. The x squared term dominates. Positive again. Plug in a number, let's say 3. We have 27 minus 54 plus 24. That's negative. Okay, so we've got the same situation. Increasing, decreasing, increasing. This is our function, which means that there's a local max at 2. So f of 2 is our local max, and a local min at 4, meaning f of 4 is a local minimum. So that's how we do this. Now the functions could be more complicated. We've got to sit down, find these critical numbers, but we're starting to see how we can use this derivative to get properties of our function.